I would say you can go ahead anytime.
Cool. Well, welcome everybody. Got one or two more colloquium left for us this semester. I'm very happy to introduce today Ken Takahashi. Ken has a PhD from the University of Washington in Seattle in atmospheric sciences, where he specialized in large-scale tropical coupled ocean-atmosphere processes. It's that body of work of his that I'm most familiar with. He did some really fun GCM work with flattening the Andes to see what kind of climate dynamics the Andes have, which is something that I've always thought was so cool. After that, he was a postdoctoral researcher at Princeton, at NOAA GFDL. He worked on physics of global climate change, so issues with ocean heat uptake and equilibrium climate sensitivity. Now he's back in his native Peru. His research is focused on the physics of El Nino, its regional impacts, and its prediction. As a member of the Peruvian National Commission for El Nino Study, he played a key role in establishing operational procedures, as well as in informing stakeholders, decision makers, and the general population with respect to scientific issues. He is currently the director of the Peruvian National Meteorological and Hydrological Service. He's a member of the WCRP Joint Scientific Committee, the permanent representative of Peru with the World Meteorological Organization, the WMO, and is a member of the WMO Executive Council. So I know we're all, far away and not in the same place, but yeah, let's have a warm welcome for Ken.
Well, thank you, Elizabeth, and thanks everybody for this opportunity, for this invitation. It's actually nice for me, as I was telling you earlier. I mean, I've been kind of away from the research activities for some time since I took over this new position at the Meteorological and Hydrological Service, but I'm very interested in still, collaborating with others in some of the issues we find to be particularly important for us to get more and more research. Because these research, particularly the issues I'm going to be talking about now, have a very direct impact on the well-being of my fellow Peruvians. So let me try to share my screen so we can start with the presentation. So my title is Extreme El Nino in the Far Eastern Pacific. Far Eastern Pacific means along the western coast of South America, where Peru is located. And the El Nino for us in Peru particularly means not only warmth, like the warm ocean, but also very heavy rainfall in the otherwise dry coast. It's pretty much a desert along the coast of Peru, but as you can see in the picture, this is downtown, the city of Piura in northern coast of Peru. This is supposed to be like the streets and the main place. So, the river overflowed, and this took place actually during the 2017 coastal El Nino, which I'm going to be talking more about next. And these are a couple of other views of other parts of the coast of Peru during that same event, the same El Nino event, which was pretty much the earlier part of 2017. As you can see, very, very intense flooding downtown Trujillo, and also Lima is the capital city, and this is a view of one of the aftermath of one of the mudslides that wiped several settlements. So this is kind of what we're concerned about, and the research I'm going to be talking about right now is going to be structuring the following items. So the first one is El Nino diversity. So the types of El Nino and how this diversity impacts coastal Peru particularly, but also the interior of the country as well. I'm going to be talking about the extreme global, like ENSO events, which we all know pretty well, I guess, worldwide. But also, I'm going to be focusing a little bit more on the extreme aspect of those El Nino events and why I think they are particularly, or they have particular physics that we have to make sure we have well represented. Then we have the extreme coastal El Nino, and the coastal El Nino is kind of a new concept that's popped up since, I guess, 2017, but it's actually an old phenomenon. A phenomenon that we had known very early in the El Nino, when El Nino started to be part of the a legitimate research question worldwide, but we kind of forgot about those. So now we're kind of trying to bring them back. And finally, I'm going to be talking a little bit about how these different aspects affect operational activities for particular climate prediction. So first of all, start with what we call the beginning for El Nino research, I guess worldwide, but particularly in Peru. So these are two articles from 1891 and 1893. The first one on the left is talking about an event that was observed in 1891, which was featured warm ocean currents, humid and hot atmosphere, heavy rainfall, flooding. This was a very extreme event for Peru. It produced a lot of impacts. But at this point, we didn't have it characterized as a climatic anomaly or a climate event. And actually, a couple of years later, then we had this first naming, I guess, of the phenomenon as the corriente del niño, the child's current. As I say, probably because it was more evident after Christmas time. So for us, would be during the warm season, and this current became now a topic of study, not just in Peru, but also internationally. There was a lot of interest in trying to now characterize the past of El Nino. So, I mean, having to have an idea of how anomalous this event is. And then since the initial concept of El Nino began in coastal Peru, not just with a warm ocean current, but also with the impacts in terms of, say, heavy rainfall or flooding in the desert area. Now looking at documental data, I guess, it could be newspapers, chronicles, or whatever we had available. Several authors, and particularly Quinn, was able to establish chronologies of El Nino events based again on the coastal El Nino impacts. And in this picture, we're seeing some of the most intense, the strongest impacts, or the strongest events highlighted in darker bars and with the years in red. And this study was published in 1992, so it didn't include 1997, 98, or actually in 2017. But you can see that the last very strong event was in 1982, 83, and the previous one was 1925, 26. And before that, 1891. Now remember, 1891 was the one that gave the origin to the El Nino research. And before that was a very strong event, 1877, 78. And I'm going to stop it there. I don't want to enumerate all the events, but these ones are particularly important for the research that came afterwards. Now, these are instrumental data from northern coast of Peru. At the top, we have the Min River, Piura River discharge, the same river that flooded the city of Piura in the first picture I showed you. So these you can see that these years are very different. We have a huge interannual variability. Most of the years is actually pretty dry, but some years like 1998, then 83, 2017, and 1925 really stand out. I mean, these are not relatively large anomalies. These are like a different climate altogether. And below we can see a sea surface temperature measurement at Puerto Chicama, which is another site on the coast of northern coast, but a little bit to the south. But still, you can see a very good correspondence between the two time series. So particularly when you have very wet years, we also tend to have very warm years. And again, you can see the variability in the SST is huge. I mean, we're talking about values ranging from around 15 to 25 degrees C. So it's larger than the seasonal cycle. And one interesting year I wanted to point out is 2016, because most of you probably know 2015-16 as a very big El Nino. And you can see that it indeed was warm. You can see that the SST was high. Not as high as in 2017, but still pretty high, but it was dry. along the northern coast of Peru. So this was a weird year for us in terms of prediction. So I'll talk about this a little bit later. These are the precipitation anomalies in Peru. I mean, this is a gridded data set we compiled based on station data. And you can see the blue regions are where the precipitation was very, very high above normal. And you can see that the northern coast of Peru in the three cases, 83, 98, and 2017, all have this common feature. Elsewhere in the country, the anomalies were not as similar. One important impact of El Nino, of the large scale, say El Nino, is the drought in the southern part of the country in 1983. And this, we believe, is a robust teleconnection of El Nino, but still, as you can see, it's not always manifested the same way. And in fact, 2017 had kind of the opposite because we had a very wet southern part of the country. So it kind of makes us wonder what are the typical effects of El Nino beyond the rainfall in the northern coast. Now, if we look at these four biggest events, the last four biggest events, which are 1925, 1983, 1998, and 2017, you can see that the patterns of the sea surface temperature anomalies are very different. I mean, you can group them in two very different classes. The ones on the left, the global or the ENSO El Nino. I mean, this is pretty well known. You have warm anomalies along the coast of Peru, extending along the equator to the center. But then on the right, we have what we're calling now the coastal El Nino. And the coastal El Nino, I mean, by its name, the SST anomalies, the positive SST anomalies are quite restricted to the coast, whereas along the rest of the equatorial Pacific, it's between neutral and even a little cool. And by the way, these plots are have removed all the tropical means, so you can see the patterns more clearly. So you can see that the two on the left and the two on the right are very clear members of two very different classes. So, and both of these are very important in terms of their impact for Peru. And I want to point out 1891, which was the other, the first, I guess, very strong El Nino event. I mean, the first reported actually in the international, in the scientific literature, was actually also a coastal El Nino. So these are not new type of events. I mean, these are the old type of events. Kind of, we just had a more recent case, but after a long time, but it's not new. So I wanted to talk a little bit about the evolution of the El Nino concept, not El Nino itself, but the concept of El Nino in the scientific community, just to kind of let you understand where we're coming from in Peru, where we're coming from when we talk to the international community about this. Because we had the original research of El Nino, the original publication on the 1891 El Nino, was focusing only on this southward warm countercurrent, El Nino current, which was limited to the coast of Peru and had very heavy rainfall and flooding, etc. And then 1925, which was the next very strong event, also coastal. And for this event, this oceanographer Schott from Germany, he postulated that the origin of this event was the northerly winds that were observed that year. Northerly winds that presumably drove the warm water towards the south and initiated the event. Now then, I mean, that was the prevailing view at that time, but then after the years went by, and finally when Bjerknes came around, and he proposed that it's the ocean atmosphere coupling, but on the very large scale along the equatorial Pacific, and particularly associated with the east-west swings of the Southern Oscillation and the zonal winds that push the waters from one side of the Pacific to the other. Then the paradigm, the concept of what El Nino is, was very tightly then linked to the idea of the ENSO phenomenon, the Niño-Southern Oscillation, which is intrinsically coupled ocean atmosphere phenomenon, but in the zonal direction from west to east, not north to south. And after that, then the idea of Schott in 1931 was put down and discredited. Further on, then the 1982-83 El Nino came. By then, we had the composite El Nino from Rasmussen and Carpenter. This event did not conform to that composite and made people question whether some aspects of that composite event were indeed essential. Particularly the warming at the coast of Peru was not seen then as a necessary precursor, which was believed to be by Rasmussen and Carpenter. And it kind of started a shift of maybe El Nino is not just the coastal warming along the coast of Peru. So eventually that led to the introduction of in 1987-98, actually, during that El Nino of the Niño 3.4 index, which is currently the dominant index for monitoring El Nino worldwide. And I mean, then it makes sense. I mean, this index is very good for two applications. One is characterizing the state of ENSO, because this index also correlates very well with a Southern Oscillation index. So it gives a good representation of the basin-wide variability. But also this index has a very good correlation with climate impacts worldwide. So it was a very effective, very efficient index. But obviously for Peru now, the Niño 3.4 is not the same thing as the coast of Peru. So to the extent that variability on one side and the other are not one-to-one related, then that creates an issue. Then now after 2000s, we started talking about the diversity of El Nino. Particularly, people started focusing on whether the warming was more towards the center or towards the east of the equatorial Pacific, because that makes a difference in terms of the dynamics of the impacts. And more recently now, we saw the 2017 coastal El Nino, and we actually in 2017 we published a paper on the 1925 El Nino, just before the coastal El Nino started peaking, and in that paper we tried to reivindicate the northerly wind as an important player for these type of events. So kind of coming around in a circle. Okay, so now talking about ENSO or El Nino diversity. Now, as I mentioned, people start focusing on whether the SST anomalies along the equatorial Pacific are more focused on the eastern part or the central part. And now there's several classifications that can be used, and these are all arbitrary in the end. There's no unique way of making this classification, but roughly speaking, it's this logic, either the center or the east. There's also a classification based on, say, the time, so whether it's shorter lived or longer lived, or the intensity. But this is, I think, the dominant way of classification people are looking at for the past few years. Now, we proposed with a few colleagues, we proposed a way of making this a representation of the ENSO diversity, which is just a very, very basic approach. We took the principal component of the sea surface temperature anomalies along the tropical Pacific, and we found that it's better, more intuitive, and also has a bunch of interesting properties to not just take the first two EOFs or principal components, which summarize, as I indicated there, 82% of the variance, but to rotate them in the PC space so that we have a new pair of indices now, which we're calling the E and the C indices, and that are associated with, in the case of the E index, the Eastern Pacific warming, and the C index, the Central Pacific warming. And the interesting thing about using EOFs is that by construction they're orthogonal, and we applied an orthogonal rotation, so this is preserved. And you can see, obviously, because they're orthogonal, the correlation between them is zero. I mean, that is equivalent. And it's interesting then to use these indices to represent the variability, because it allows us to cleanly isolate what is, I would say, proper of each of the two regions. And we can see, for instance, in red, I have highlighted the peak of the rainy season for the 1998 and 83, sorry, and 98, very large El Nino. And you can see that they coincide with the peak in the E index. So which is, I mean, what we expect, a very high warming along the coast, but also a little bit on the sea. So there's some warming along the Central Pacific. Now, conversely, if we look at the 2016 event, We had some warming on the eastern coast, so we have some positive value of E in March, but we also had a quite large, relatively large value of C. So this is a somewhat different pattern, because these indices represent the pattern in that event compared to the previous two. And then the last one is 2017, which is also very interesting because it also has a positive E anomaly, so warming along the eastern coast or the western coast of South America. But that event has actually a negative C index, so it's slightly cool in the Central Pacific. So it's, again, the pattern is quite different from the others. Now, these indices can be then considered to be, as I say, a representation of the pattern. And I guess it became more clear when you start plotting them one against the other, so the PC1 and PC2. And I'm sorry, this plot is probably very confusing for everybody. So first of all, you can see there are two indices, two axes, the PC1 and PC2. So these are two coordinates, I guess you can say. And each dot here corresponds to a December to February average. So each dot is a season from one particular year. And then you can use the position of that yellow dot on this plot to determine what the pattern is. The pattern, the overall pattern of the SST anomalies in the tropical Pacific. And now, because these two indices represent so much of the variance along the equatorial Pacific in particular, we can use these two to reconstruct a bunch of other indices that are more widely used. For example, the Nino 3.4 index can be considered to be, as you can see, this blue axis here. It's pretty much a linear combination of the PC1 and PC2. So essentially now you can take a yellow dot here and project like a perpendicular line towards that blue index, and you can essentially read off the Nino 3.4 value. So this is a pretty nice compact way of representing the different indices. Now, what we noticed was that in this plot, most of the data is aligned, it's not just randomly scattered, but there is some alignment along the diagonal, which reflect the C index. And then there's these few events that kind of jump out of this cloud of dots towards this diagonal to the bottom right. So we decided to, why we decided to rotate the axis into these two directions, the E direction and the C direction. And and as I said, the E corresponds to Eastern Pacific and the C to the Central Pacific. So you can see around the plot also the different patterns that go with each of these axes. So now the interesting thing we find from this is that since most of the events are along the C axis, and we have the extreme La Niñas towards the bottom left. But if you go to the top right, what we have is moderate Central Pacific events. And only when you go off towards along the E axis, when we have these extreme El Niños, which are more focused on the Far Eastern Pacific. And as you can see, the three largest events in the sense of the E index are the 8398 and 1878 event. And again, the 2016 El Nino was pretty strong in the sense that if you now look at the Nino 3.4 value, it's comparable to the ones of these other three events, but the pattern is quite different because it's more toward the sea. So it's more zonally uniform, not so warm along the coast and warmer in the center. So it's more like actually the PC1 pattern here. So that produced profound effects on the precipitation anomalies in Peru. And one of the questions we had is whether the fact that these three events, the extreme El Nino events in the Eastern Pacific, are actually that far apart from the rest because there is something else going on. Particularly, we're thinking about maybe the dynamics are somewhat different. And if so, then obviously, what are those, and can we use this knowledge to improve our prediction of the El Nino? So now we started working on trying to understand these the extreme global ENSO El Niños. And since two events, and because 1877, 78 doesn't have as much data as the 83 and 88, but still it only leaves us with two events, which is very tough to use for coming up with statistics. So we found that the GFD-LCM 2.1 model, the climate model, actually had a very similar representation of the El Nino, these extreme El Nino events as the observed, which you can see here in the diversity of normalized indices, say for the E and the C, the heat content, equatorial heat content, the thermocline tilt, the zonal wind stresses. And in the blue and red, you can see the observed indices, and the black lines are essentially the distribution of the extreme events in the GFD-LCM 2.1 model. So we can see that, roughly speaking, there is a very good correspondence between the model and the observed. So we had some confidence that the model was reproducing something close to reality. And one of the interesting things we found that supported to some extent our hypothesis that there is some sort of a double, say, dynamical regime in El Nino, is that, again, if we look at this bottom right plot, where the darker dots correspond to observations and the lighter ones correspond to the model, you can see that these contours, which correspond to the empirical probability distribution function for the models, for the GFDL model, has actually a bimodal structure. So it's not just an elongated distribution, but actually has like two modes, which we, well, obviously named the strong El Nino and the moderate El Nino, and with a cutoff somewhat a separation, not so much a cutoff, but a kind of like a separation at around 1.8 in the value of E, not so much in C. So this suggests that something is going on in the Eastern Pacific that allows that whenever we go above some value, something else starts taking over, and the El Nino become stronger or faster than they would otherwise. And in this, looking at the data, and also in the GFDL model, we found that the one very likely candidate for explaining this is that as the Eastern Pacific warming goes up, the convection in this area and also the wind stress, as expected, will go up. But once you go above some value of warming, around 1.5 in the case of the E index, then the rate at which this increase happens is 3 times as larger than the one below. So this implies that the feedback, say the Bjerknes feedback, what we call the positive feedback that allows El Nino events to grow, becomes much stronger as you go above that threshold. And if that is the case, then we could suspect that this will imply that the El Nino could grow much more and become larger than otherwise it could. And we actually tested this, kind of like a educational exercise by coming up with this heuristic theoretical model based on the Feifei Jean's recharge-discharge model. But we added a small tweak by including a nonlinearity in the coefficient, the damping coefficient of temperature, of sea surface temperature on itself, which is this coefficient A in the matrix up here. So what we did is that in this model, which is a stable model, it's a damped model. So this A coefficient is actually negative because it's bringing variability down. Whenever the temperature goes above a threshold, which we call T sub C, then that damping goes to 0. So it's a very, say, conservative way of altering this model because it's still stable. So it requires external forcing to keep the variability going. So that's what we have here on the right-hand side. This term here is the stochastic forcing, not just noise. So weather noise that is just pushing around the system. So all we have here is that whenever we go above a temperature threshold, the damping of temperature on itself goes to 0, no damping, so just neutral. Otherwise, it is just the same model. And the value for this threshold is approximately 27.5 degrees C. I mean, you kind of estimated that by assuming that the T variable here corresponds to the Niño-3 index, SST index. And so T sub C is around 1.5 degrees C. So with that, we can test how the model behaves compared to observations. And these are plots on the what we call the phase space. So temperature versus H, which is the heat content. Sorry, I didn't mention this, the ocean heat content along the equatorial Pacific. So in the recharge discharge oscillator model, I mean, this ENSO will just go clockwise around the center here. And because it's damped and it's got forcing, this trajectories become very noisy, and as you can see, it's very much going around the origin very irregularly. But as you can see in the observations, once in a while we have these large excursions to the right, so very high T values, even though the H, the heat content, is not necessarily very large to begin with. Say, for instance, 82, it didn't start very high, it just became higher and warmer. I mean, higher heat content and warmer at the surface simultaneously until it was very high, and then it just started discharging. So the heat content went down and then came back to this blob here. So very similar to the case of the 97, although that one did have higher heat content to begin with, and then it became warm at the surface. Now in the theoretical model, this is more regular, I guess. And the behavior here is quite similar. Again, it does not necessarily start with a very high heat content before going to the surface warming. Actually, you can start up here relatively low heat content and just go straight to the warming and then discharge, and again going back. Although in the model there is a tendency to have very strong La Niñas after the big El Niños, which is not something we see, at least in this in nature. I presumably, to some extent, this is because this model is not considering the spatial diversity, in which La Niñas tend to be more to the Central Pacific, not in the Eastern Pacific. So I guess this model is just showing that it is possible to get a very similar behavior to the extreme El Niño just by taking that nonlinearity in the feedback parameter for the discharge model. And this is a kind of like a summary of the behavior of that model. This is again phase space T versus H, and in the red lines, what we have is the mean trajectory in phase space of the extreme El Niños. The solid curve is the model, and the dashed or dotted curve is the observation. So the two very big events we know of. And the green lines, and this is, I guess, very interesting to see in this way. The green lines are the deterministic trajectories. This would be what the physics of El Niño, of the research oscillator model, would produce without external forcing. And what I think is interesting is that you can see that they're almost orthogonal to some extent trajectories here. So the deterministic trajectory is saying that the system would just go to discharge and then start to cool, but the actual model, the actual El Niño, is just keeping its heat content going warm and warm and warm. So this implies, I mean, this means actually that the way the model is getting towards from the cooler towards the extreme El Niño is by the external forcing. So it's not that the system just gets triggered and just goes off, but it has to be pushed and pushed and pushed. It requires absolutely sustained forcing, low frequency forcing. It's not enough to just get like a month-long pulse. It has to be sustained at low frequency. I mean, we actually made a bunch of experiments on how this nonlinearity and the stochastic forcing would interact. Actually, the very high frequency forcing, say the monthly variability, cannot actually drive the ENSO variability. It's just too much of a mismatch in timescales. But it does help. I mean, if the low frequency forcing is pushing the system towards El Niño, and then comes one very short burst, say from the west, comes along, it can help push the system over and allow it to become an extreme El Niño. So it does have a role, but the crucial aspect here is the low frequency forcing, and that is something I don't think the community is focusing very much on. I mean, Dan Beaumont here has worked quite a bit on that issue, but I think most of the community is focused more on the very high frequency, say intraseasonal time scales, and not so much of the longer timescale. And then now I'll move to the coastal El Nino. And just to get, I talked about the fact that the event is localized, but it's also not just localized in space, but also in time. So in these are again from the Puerto Chicama SST time series, daily time series. And you can see here, this is not an anomaly, it's just the absolute or the total SST. You can see 1998 in the, I would say it's kind of brown or dark green here. And it was compared to the climatology, which is the dark line below here, it was very warm, very early on. And the same with 1983, which is the light blue curve. However, 2017 and 1925 was actually neutral, was very, very close to climatology until, say, January. And in the case of 2017, you can see here from mid-January to the first days of February went from almost 17 to 27 degrees C. So in a couple of weeks, 10 degrees C warming. Then it cooled again a little bit, I mean, not too much. And again, another peak here later in March. So it was very abrupt, but also in the event lasted from, say, mid-January to roughly mid-April. And similarly with the 1925 event, this was somewhat more, started later, but by the beginning of March, it went from 20 C to around 27 degrees C. And it had a very warm period, and then it collapsed again. By mid-April, it was pretty much gone. And during this warm period is when all of the impacts of the coastal Nino took place in northern Peru. So very short, and we live very, very tied to the warm season because of the dynamics of the ITCZ, the intertropical convergence, on which I'm going to be mentioning more about later. So this is this from the study we made on the 1925 event. You can see here the March climatology for the period earlier in the 20th century. See in March, what we have is an ITCZ on each side of the equator. Weak ITCZs, intertropical convergence zones, northerly wind going toward the northern one, southerly winds toward the southern one, and pretty much calm winds in between. But in March 1925, what we had was just northerly wind across the equator into this strong ITCZ south of the equator. And this is again March 1925 when all the flooding and the heavy rainfall took place. And this is actually quite similar to what Schott found for 1891, the 1891 event. Again, this is all based on ship data. And you can see in his sketch, the northern winds went all the way to 5 degrees south, which is Piura, which is the normal location of the southern branch of the ITCZ. So I mean, in this case, he depicted the ITCZ somewhat slanted, like this. But I think the data is probably more reliable near the coast anyway. So it's quite consistent with what we find for 1925. And another thing we found for the coastal El Nino is that the ocean dynamics, particularly the equatorial ocean dynamics, which is primarily associated with equatorial Kelvin waves, was not prominent at all. I mean, there was very little evidence from the data we had, particularly from the sea level gauge at the entrance of the Panama Canal here. We can definitely see Kelvin waves there when they are occurring, but for the 1925 event, we had very little evidence of any Kelvin wave. Instead, it seems more like it's a local process associated with the northerly wind and the shift of the ITCZ, or actually I would say the transition from a double ITCZ regime to a southern ITCZ regime. And this meridional process, this meridional feedback is what's probably key for the coastal El Niños. And one aspect of this type of events that is helpful for this fast growth is that the ocean warming is very shallow compared to the, say, ENSO. So in the plot on top, we can see the anomalies near the coast of Ecuador during the, let's say, the 90s and early 2000s. You can see the anomalies for the 1998 El Nino extend all the way to the bottom, well, around 100 degrees, 100 meters deep. But for the coastal El Nino, and this is another site for a little sort of further to the south, actually, at the latitude of Piura at 5 degrees south, we have the warming taking place at very shallow layer, just 30 meters or less, at least at the beginning. Then, as the event was maturing, and then we got deeper anomalies. But the onset and when most of the impacts took place was actually very shallow warming. And this means shallow means faster, means less water to warm up. And actually, Vincent Chevin and his co-authors made some nice ocean model experiments, and they tested the different effects where that could lead to the warming. And they, for instance, they shut down the wind variability, they shut down the equatorial Kelvin wave variability. And what they found is that the wind effect is largest by far. So it is the fact that the circulation changed locally that drove most of the warming. But later on in the event, along the event, the ocean Kelvin waves did have a role in producing extra warming. So this kind of this supports the idea that this is quite a local process, and this has obvious consequences for the predictability of such an event. And now the counterpart of that study is the one that Peng et al. Made for the atmospheric response to SST. So in this case, they imposed SST anomalies into an atmospheric model, and they found that just imposing the local coastal SST, like in this bottom left plot here, what they have this enhancement, local enhancement of precipitation, and this northerly flow, and also they get some westerly flow, also anomalous flow. And if you look at the meridional plane, what they have is that the circulation is actually extended throughout the troposphere. So we have the northerly flow near the surface, bringing in, or actually associated with more moisture in the southern hemisphere, where the convection is taking place. This flow is going up in the convective areas and going back on the higher level. So it's kind of like a local Hadley circulation cell. And this is the one they found from the model for the observed ST for the coastal El Nino. And the reanalysis data shows a very similar picture. Dry in the northern hemisphere, wet or moist in the southern hemisphere, going up in the convection cells. So again, this highlights this local type of circulation response, and bringing the two of them together, the ocean and the atmosphere, puts together a picture of ocean-atmosphere interaction that is in the meridional plane and local. So some implications for the operational activities. I mean, now I'm at the National Meteorological and Hydrological Service, so this is very relevant for our operations. First of all, we talked about the ENSO diversity in the patterns. We wouldn't really care about this unless it had an impact on our country itself. And indeed, if we look at the effects of the Eastern Pacific warming, this tends to produce enhanced precipitation along the coast. But if we have Central Pacific warming, this has a drying effect along the Andes and the mountains that are going just east of the coast of Peru. So very opposite effects of two types of patterns that are both considered to be El Nino. So you can see how this could be confusing for the population, for decision makers, for even the scientific community in Peru, to have El Nino have opposing effects in the same territory. And of course, I mean, these two patterns are not exclusive, and they can happen simultaneously. And it's a matter of which is bigger. I mean, we could now have one of those to be positive, and the other ones to be negative, and so on. So a bunch of different combinations of the two, and the impacts in the country are going to be different accordingly. This is a similar type of analysis, but now we're looking at the whole South American continent. On the left, we have the typical correlation with Niño 3.4. Red is drier, blue is wetter. And if we look at the other two patterns, we have the C and the E correlations. And here we see that essentially what we find with Niño 3.4 is separated into two aspects, say for C and E. particularly E takes care of the wet conditions along the coast of Peru and Ecuador. C takes care of the drying in makes most of the tropical Amazon region. The C both contribute to the wet conditions in southeastern South America. So this could be useful. I mean, to the extent that we have predictions of C and E or equivalent indices could produce more detail in our seasonal predictions if we had this information. Now, it's not always as simple as, I mean, we've just been talking about linear correlations, linear relationships, but this is from the study we made for 1925 event, but here we're looking at the time series of the Piura River discharge again, we saw earlier, and how it correlates with SST anomalies along the tropical Pacific. And we see that, I mean, there is obviously a high correlation near the coast, with SST near the coast, particularly in the Nino 1+2 region, but there are also negative correlations in central Western Pacific, which could be, I mean, does not necessarily mean that there's a causal effect from this region, the remote region, to the coast. I mean, it could just be a reflection of the typical pattern of ENSO, but it have no causal correlation. But indeed, I mean, we combine the two, it produces a better fit to the observations, and that we can see in the scatter plots below. I mean, if we just show the Nino 1+2 warming versus the river discharge, we see, I mean, the warmest years have the strongest discharges, but that relationship pretty much breaks down for the milder events here. And actually, if we just plot it against the central Western Pacific region, the extremal Niños are kind of in the middle of the distribution, but then we have this kind of almost like somewhat of a hint of a negative linear relationship for the ones below. So if we take the difference between the two, the Eastern Pacific minus the Central Western Pacific, and use that as an index, then we have this nicer, I guess, relationship in which the wetter events are also lined up with the, say, warmer events, but warmer in terms of a gradient. And this kind of makes sense because what matters for precipitation is not the absolute temperature. I mean, absolute temperature matters, say, if we're talking about actual water content in the atmosphere via the Clausius-Clapeyron relationship. But we think that the main effect here is more on the stability of the atmosphere. So, I mean, the Eastern Pacific is cold and is stable, but whenever you have the surface warming relative to the warming above, then that can help convection to break out. And we think that this index in the Central Western Pacific actually is a measure of the conditions in the free atmosphere. So this gradient between the east and the center west is a proxy for the vertical gradient. So it makes more sense. I mean, it's kind of like a stability index in that sense. Now, in terms of prediction, climate models are pretty good for predicting the ENSO at this point. We still cannot trust fully the models, particularly if we're thinking about the magnitude of the warming in the Far Eastern Pacific, because as you probably know, there is strong biases of the models in this region. They're too warm. I mean, in the mean, they're too warm and too wet. So that must have an effect. I mean, we don't really know how much or exactly how it works, but we expect there to be an effect. And we can see that in the somewhat weak variability we see in this region in the models. And so we're still looking for, say, empirical type of predictors that can complement this, complement the prediction in real time. So in this study we did with the climate, the GFDL climate model, we analyzed these extreme El Nino events based on the index, the Eastern Pacific Index, and we found interestingly that that heat content, which is the plot on the left, the heat content, say around August, and going in this axis, does not really present a very good correlation with the warming of the Eastern Pacific in the next January. So a few months after. I mean, there is association here in the sense that if we have heat content below, say, -10, then there's pretty much no chance that we'll get a strong El Nino in January. And if we have, say, above 0, pretty much anything could happen. So we cannot rule out extreme El Nino if we have positive heat content. So it does not determine what the outcome is going to be if we have positive heat content. On the other hand, if we look at this other index, which is the zonal wind stress in the central part of the Pacific, if we have a value, say, here roughly around above 3, this is a normalized index, by the way, around 3, both the observed and the model, the GFDL model output, are all saying that there is going to be a warm year in the Asia Pacific, a very warm year, actually. So this looks more like a predictor of extreme El Nino. And at this point, I mean, we have the models. We can believe that to some extent they're realistic in the sense that they line up with the observed, but still the observed is what should matter the most. And there's only 2 events here. So this paper was published just in 2015 as we were making the forecast for 2015-16 El Nino. So we had a chance to test this in real time. So we made a prediction and it turns out it worked pretty well, actually. So this is what 2015, the prediction looked like. Not as warm as the 82 or 97 or 98, 83 and 98. And this was a problem for the rainfall prediction. Why? Because if the warming along the coast was milder than 97 or 98 or 83, then meant that the effect of the local effect on enhancing rainfall was also reduced. And in fact, 2016 was a dry year. I mean, drier than usual. So the impact of El Nino was the opposite to what it was expected. So we nailed to some extent the temperature forecast, but the rainfall forecast was not good in that sense. We believe that, I mean, this was cooled probably because of the southerly trade winds that were quite strong during that period. I mean, we noticed that, but we could not explain it at that point. But in the end, well, it turned out that way. So as they say, 2020 hindsight, well. And this is from a paper we published with my colleagues at NOAA, my colleague at NOAA and the Bureau of Meteorology in Australia, and trying to recapitulate what happened during that prediction. And one of the things we documented here is that 2016 was actually one of the warmest events in the Central Pacific. So if you look at Nino 4, it was the warmest. And there's a trend, global warming component to this. So it's not purely the Central Pacific that was warm, but still, we feel that the gradient between the east and the west, or the east and the central Western Pacific, was reversed for this event. So you can see here the pink bar here is representing the rainy season in Peru, in northern Peru. And even though 2016 was warmer than the 73 El Nino, it was not almost half as warm as 98 or 83, but the 2016 warming in the Central Pacific was twice as the other. So the gradient was kind of going the opposite way, and the outcome was what you can see down here in the maps, in which for the 97, 98 we had very wet Western South America, Western equatorial South America, but dry in the case of 2015-16. So it's a challenge now of how to go beyond just saying, well, it's going to be a warm year. Well, now we have to predict the pattern, not just how much it's going to warm, but how much it's going to warm here versus there, and see and make a prediction on climate, or say on precipitation anomalies based on the balance between the two regions. So, well, this is from the same paper, just to illustrate how the different countries they have different operational procedures. In the case of Peru, which is the one I wanted to focus, which is down the left, essentially we're monitoring El Nino both on the Nino 1+2 region and the Nino 3.4 region, because both regions affect our country and they affect them in opposite directions. So For communication to the public, it's challenging to say the least, because now we have to talk about the coastal Nino or the central Pacific El Nino, and hopefully people will understand what we're talking about. But that's the way it is. It was an issue, particularly in 2017, because we had this very, very strong event along very close to the coast, very warm. Yeah, I show that 10-degree warming along the coast itself. But in the rest of the Pacific Ocean, it was neutral. So while in Peru, we were already issuing a coastal Nino watch and then a coastal Nino alert, because it was very warm and it started to rain a lot. Still, internationally, this was not recognized. I mean, WMO was still talking about neutral conditions and had no real no information about what was going on at the coast of South America. I mean, and the issue here is the concepts are, I mean, they're already kind of settled on this idea of the basin-wide warming focused primarily in the Central Pacific and the Northern Pointer region. So that becomes more of an issue because now we have to explain why WMO is saying such other thing, or even know what this is too. And this is, I mean, I'm talking with my colleagues, I mean, we know this is an issue, and it's an issue every country has to just see how they can solve. Now, talking about predicting the 2017 coastal Nino, I mean, we were looking at I forgot to translate this. We were looking at the North American multimodal ensemble, which is a very nice tool. But none of the models in the ensemble predicted the coastal Nino. I mean, neither the warming or the precipitation. I mean, these are very good models for the ENSO scale phenomenon. As you can see down on the right, sorry, each color corresponds to the forecast, the ensemble mean forecast made at a different month initial conditions. You can see pretty much lines up, going from negative towards neutral and a little warm. But for the coastal Nino 1+2 region, the forecasts were just like refusing to acknowledge any warming at all. So if they started warmer, I mean, they started warmer every month as the Nino started to settle and the coastal Nino started to settle. And the model just say, well, just going to keep the same way. They did not have this growth. Apparently, the growth mechanism that allow the real event to become warmer. So that this is an issue. Probably it's probably related to the biases we have in the climate models, the warm and wet bias. So it's already too wet, maybe it just cannot get wetter. That's one possibility. Or too warm, it cannot get much warmer. So there's still work to be done on this issue. So that's it. So just to summarize, the extreme El Nino in the Far Eastern Pacific, I mean, talking about warm and wet conditions pretty much along the coast, can be classified in two types, the global ENSO and the coastal events. And the coastal event is not a new type, it's the older of the two. The nonlinear enhancement of the zonal Bjerknes feedback and aided by this low frequency forcing, these two, we believe that can be the main elements behind the El Niños becoming extreme, the large-scale El Niños become extreme, particularly in the Far Eastern Pacific. But for the coastal Nino, it's more like the meridional ocean atmospheric coupling. And here it's an example, I mean, it's kind of well-known, the west feedback, the wind evaporation SST feedback. Not necessarily the same thing that's happening exactly here, but I mean, this study of with ocean modeling for the coastal Nino, they were talking mainly about the dynamical effect of the winds on the ocean, say particularly affecting the upwelling or the Ekman pumping that can deepen the thermocline and therefore lead to dynamical warming of the ocean, not just surface fluxes. But still, I mean, the basic idea is that the atmosphere and the ocean interacting in the meridional direction is probably the key for the coastal Niños. And the challenge is because it's local and it's very fast, then can it be predicted? I mean, that's something that we still don't have a clear idea about yet. Then, as we were looking at the different regions in which we can have the warming or cooling in the equatorial Pacific, these can have even different signs of the impact in terms of precipitation in Peru. So it becomes challenging for us to communicate, or even actually to make the predictions to begin with, but also to communicate. And as I said, we need more research on trying to improve our predictability or our prediction skill, particularly of the coastal Niño. It's possible that predictability is limited. So theoretically, potentially, even we're already limited to maybe 1 month or something like that. But still, I mean, we think we have to keep looking, and maybe we'll find something that can next time allow us to make a prediction, not just with 2 or 3 weeks lead time, but maybe a couple of months. That would be nice. So again, thank you, and that's all I had to give you. Thanks. Oh, by the way, there is this new book, the AGU book, in which we have an ENSO diversity chapter. I think it's a pretty nice book. So if you have a chance, you can take a look at it. Thank you.
Thanks for the great talk. As you can see, there's lots of little virtual clapping buttons appearing. Since we can't actually clap, I guess I'll clap so someone can hear me. We're actually at the end of our hour, but we can stick around for a couple of minutes to take a couple of questions. If you have to go, that's fine. So I'd like to open up the floor to questions first from students, if there are any students, and then to Dan.
But by the way, I have no problem staying. So
cool, that's great. Students. I'll give it another couple of awkward seconds. Okay, I'm going to let the students ponder that one and I'll come back to them. Dan, what's your question?
Sorry, I got to come off mute here. Sorry, I got about 90 questions. This is an outstanding talk, Ken, and you know, the stuff you showed here. You showed an immense amount of stuff. I think it's some of the neatest El Nino related research that's going on right now. So I really appreciate your talk. I guess the related to the NMME's inability to capture the predictions, as well as just in general simulating these, how well do those models capture these in, say, a climatological simulation of the models? Are we, these models have such biases in the Eastern Pacific? Are they able to capture the events at all in their say just mean state simulations or climatological simulations?
So I mean, my hope is that there is some signal in the GCMs. I mean, it's probably going to be very muted, I mean, compared to the actual thing, but at least maybe if we can calibrate, like say, okay, this is what the model is saying. I mean, for the model, this is what when in real life would be a coastal El Nino. So if we could find that in the model, maybe kind of like applying somewhat like what called the MOS technique, the model output statistics technique, something like that. But the problem is the sample size, right? Because I mean, I'm talking about a coastal Nino in 2017 and then a previous one in 1925. So how do you do the corrections to the statistical corrections to the model when your sample size is so small? I guess, I mean, you could kind of hope that the models have some sort of a coastal El Nino or the extreme El Nino. Actually, it's the same thing, because again, the extreme El Nino will have two. So what we did for the extreme El Nino is try to find what the equivalent is in the climate models, and we use the E and C indices, not just because, I mean, they're compact representation, but because they're come from the model itself, right? So from the model climate itself. So if the model has biases, but it still has some sort of an E pattern, which is going to be somewhat different to the real one, that is the model E pattern. So if you can at least represent let's say the internal workings of ENSO in the model world, and the model is qualitatively similar to the observed one, maybe we can do that kind of conceptual mapping from the model world to the real world. And that's kind of what we did for the GFD-LCM 2.1 model, because it was, I mean, the E and the C patterns are not the same as in nature, but the behavior of the indices is kind of like that. Even, I mean, you also have to scale them because it's, I mean, the UFs are in our calculations were normalized. But if you took the absolute values of the, say, of the variability, it's not the same either. So if you can make that mapping also for the coastal linear, if you can find something in the global models that looks qualitatively like the coastal linear, and you can establish that mapping between model and nature, maybe you can come up with some way of improving our real-time, say, predictions of them too.
Thanks. That's a, you know, it's a, the small regional areas that you're showing for this coupling with the meridional circulation for those coastal El Ninos. I mean, that's such a challenge for these models to get that, especially given the biases here. So it's a, you know, it's a, but it's very clear from your presentation just how important that is. And so it's a, you know, this is it's just an outstanding example, I think, of why we need to be dealing with these mean states in the Eastern Pacific. You know, even though you can maybe get the E, and you can do sort of an analog E index, it's not clear. I mean, it seems like it's so tightly coupled there. It's really interesting.
I think we have time for one more quick question if there is one from anyone.
I have a question.
Go for it, Andy.
Yeah. Thank you, Dr. Takahashi, for the interesting topic. I think I live in Indonesia, and Indonesia also affected by El Nino, but in a different way. Like El Nino in Indonesia is very dry, and I was wondering. Actually, I also have several questions, but I try to make it short. First, I think, yeah, this is clear about the El Nino, the central El Nino and the coastal El Nino that affected Peru. But I still wondering how the La Nina affecting the Peru. Maybe this is out of the topic, but I still wondering about how the effect of the La Nina. And also, I'm not sure about the monsoon, because Indonesia also affected by monsoon. I don't know in Peru. And I saw that the ITCZ, comparing the climatology and the conditions when the extreme El Nino happen. And my question is my second question is, what do you think about the interconnections or relationship between monsoon and this coastal El Nino? Thank you.
Thank you for your questions, actually. So the first part of your question, talking about, say, how this could be different for other parts of the world, particularly Indonesia. I mean, my message in that sense is that every country has to look for what's better suited for them to begin with. Like Nino 3.4 is, I guess, very good for North America, say for the US, which is the country who proposed the Nino 3.4 index. In the case of Peru, as I said, we need at least 2 indices because the eastern and the central part of the Pacific contribute substantially and actually in the opposite directions. Other parts of the world could just keep using Nino 3.4. And I'm not sure whether Indonesia is also affected by say, the Indian Ocean dipole, which I know for Australia is quite important in terms of even for operational prediction purposes. So I guess it's a matter of identifying even what are the, say, relevant indices or patterns or phenomena for each country. Maybe ENC could be well suited. I mean, they kind of capture a lot of the variability along the equatorial Pacific, but not enough. Actually, the coastal El Nino is not that well represented, captured by the E index, because the E index has a pattern that is large scale, so it extends substantially to the west. So that pattern does not match well the coastal El Nino warming. So I'm not, I mean, I didn't mention this, but even if you look at the scatter plot for the E versus C the, the the coastal Nino does not clearly appear as a here, like here. It's almost near the extreme La Nina, which is kind of like what the international community was looking at the time. I mean, it is La Nina. We're coming out of La Nina. Nobody was looking at this in very narrow fringe near the coast of Peru, and this actually is also reproducing that kind of a bias, a large-scale bias, I guess, in the eye of the community. So, I mean, it's possible that there is also local effects or very particular effects of phenomena for a particular region again, and that for these, let's say, climate prediction purposes, you should be looking at directly, I mean, specifically for your region. Now, with respect to the monsoon in the coastal Nino, to be fair, I mean, the research in the coastal Nino is quite limited at this point. We know very clearly what's going on. I mean, we've looked at very in much detail what happened along the western part of the country, which is where most of the dynamics of the ocean atmosphere is taking place. We haven't really looked that much at the other side of the Andes in the Amazon region where we have the South American monsoon. I really don't know whether there is an effect of the coastal Nino on that part of the country. I mean, we know that the warming, as I say, the coastal warming does have an effect, not just the coast, but somewhat more to the mountains, but to the other side on the monsoon, it's not clear. I mean, one thing I found interesting when looking at this, researching about what is known about the influence of this pattern is that apparently tornadoes in the US are affected by this kind of pattern, which is warm in the east, cool in the center. I'm not really sure what the physics behind that is. I don't know if the warming along the coast of Peru matters that much, or maybe it does play a role in how the convection is located, and that makes it a better suited to getting the impacts on that the tornado statistics. But I guess if you're, I mean, I would start from the target, which would be in this case tornado, and look for the best pattern for predicting that, rather than going from the coastal Nino trying to figure out what else it hits. Right. So I guess those are two complementary ways of looking at the problem. I think neither of those exclusively is going to be better than the other one. I think you have to look at both. Yeah.
Thank you so much.
Thanks again for the great talk. If there's any students or other faculty who are interested in meeting with Ken tomorrow, do let me know. Let's give another virtual round of applause, and I will see some of you tomorrow.
Thank you.